Hello everyone, welcome to David Griffiths Electrodynamics. This is going to be problem 4.3 from the book. All right, so our problem statement is the following. It says according to equation 4.1, which is this one here that relates the dipole moment P to the strength, or the induced dipole moment P to the strength of the applied electric field that induced that dipole moment. According to that equation, the induced dipole moment of an atom is proportional to the external field. This is a rule of thumb, though, not a fundamental law. So in theory, suppose, for example, that the charge density of the electron cloud, instead of this one up here that we had from the previous problem, suppose it was just proportional to the distance from the center. So like some constant times r. Out to the radius of the atom r. To what power of E would the dipole moment be proportional to in that case? So because, in reality, the charge density is something along the lines of this, you end up getting this relationship. But if the charge density were proportional to the distance from the center, what power of E, how would that change this equation essentially? Would it be still linear, or would it be something else? So that's kind of what we're playing around with. And then it says to find the condition on the charge density. So what charge density then would you need? How would you need to adjust the charge density that we started with such that this equation does hold? So how would you need to adjust the charge density to then make it linear again? So anyways, let's toy with this idea. So we assume that the charge density is a function of r, and it's just going to be proportional to the distance r from the center. So we're going to use the proportion constant of a. So our charge density is just a times r. Now, I'm going to use the fact that we're probably going to want to figure out what the strength of the electric field is in this case. And given that this charge density is proportional to the distance r, then we have this symmetric sort of charge density. So the integral, we can use Gauss's law to figure out what the electric field is going to be here. We only have to figure out what Q is. So the integral, the flux integral here of E dot dA, well, E is going to be constant for any given radius r. So whatever our Gaussian surface is, that radius, the electric field should be constant, since it's only, we're going to just have this radial electric field here. And so this is just going to be E times the surface area of the sphere, which is 4 pi r squared. So the left side of Gauss's law just ends up being E, because it's a constant, times 4 pi r squared, where r is the radius of our Gaussian surface. The hard part is going to be just doing the actual other side, where we need to figure out what Q enclosed is. But the charge enclosed is not just, we have to integrate over this charge density here. So kind of like from the last problem, except we have a simpler function here. So this is going to be equal to 1 over epsilon naught times the integral from r prime equal to 0 to r of a r primed, and then d, and then we were integrating this over a oh, I see. Okay, yeah, we're integrating this. We have to integrate the volume. I was like, it should be a triple integral, but I wrote down here that doing the theta and the phi integrals, there's no phi dependence, so that phi integral would be the integral from 0 to 2 pi of d phi, right? This should be a volume integral, so you could write the integral of rho d tau, and then you'll get the phi integral, the theta integral, the r integral, but the phi integral just ends up being 2 pi. The theta integral would just have a sine of theta d theta in it because of the d tau term, and that would just end up being 2, because you're integrating from 0 to pi over the whole sphere. And then we're just left with the r integral. So that's why there's a 4 pi here, because 2 times 2 pi. And all we're left with is r squared dr from the d tau term times, or r prime squared dr prime times r prime from the charge density here. So really what we're integrating is r prime cubed dr prime. So what we end up getting here is, on the left side, we have e times 4 pi r squared. On the right side, we have 1 over epsilon naught times a, which is a constant, times 4 pi, constant, times r to the 4th over 4. Because just doing the integral of r cubed is just r to the 4th over 4. Plugging in the bounds, you're left with just the r, and the bottom bound goes away. So then you're just left with a pi r to the 4th over epsilon naught when you cancel terms. Then dividing 4 pi r squared over, the electric field in this case then is equal to a times r squared over 4 epsilon naught. And of course, when the atom is polarized and it's come to that sort of equilibrium due to the induced electric field, then the strength of that induced electric field needs to be equal to the strength of the applied field. So the induced electric field should have a strength of a d squared over 4 epsilon naught, where d is the polarization distance, that separation distance that is happening due to the polarization, due to the applied field. So then we can get an expression for d here, and relate this back to the dipole moment P. So d is equal to the square root of 4 epsilon naught E divided by A. So the induced dipole moment P is just Q times D. So the dipole moment P is just E, I'm using E for the charge Q, times 2, because the square root of 4, we just bring that as 2, times the square root of epsilon naught E over A. So effectively, when we have this kind of charge density function, the dipole moment P is actually proportional to the square root of E, or E to the 1/2 power, rather than being a linear relationship to E, which it was, previously. So this is the answer to the first part of the problem, that the dipole moment becomes proportional to the square root of E instead of being linear. But then we want to figure out, okay, how can we adjust this charge density here? How can we adjust that to have a linear relationship again? So equation 4.1, right? We know that P is equal to alpha E. So the induced dipole moment is proportional to the applied electric field. What type of charge density would give this linear relationship? So we just want to figure out what type of charge density would give us this linear relationship. So let's just assume that our charge density is some constant K times r to the m, where m is just some exponent that we don't know. Now in our case, we solved this with m being 1, right? We had a linear relationship here. But let's just assume we have some generic m, and let's kind of resolve this problem. So if we figure this out, if we redo finding the electric field here with this charge density, so let's find out the charge enclosed here. The electric field is 1 over 4 pi epsilon Q enclosed over r squared. So let's figure out what Q enclosed is. So in this case, we have 4 pi. It would still be a volume integral. We'd skip the theta. We skip the phi integral. It's just going to be 4 pi when you do those two integrals. So really, we're just integrating r prime squared times our k r to the m dr. So when you do this integral, I'm ignoring constants. What we're integrating really is r prime to the m plus 2, because of the r squared here and the r to the m, dr prime. And this is going to be r prime to the m plus 3 over m plus 3 or whatever. Like, I'm just ignoring some of these constants, so that's why I wrote this proportional thing. So what we end up finding is that the electric field ends up being proportional to r prime to r to the n plus 3 over r squared, because there's an r squared here. And so what we end up finding is that the electric field is proportional to r to the n plus 1, because the r squared cancels two of the exponents here, so we just get r to the n plus 1. So when the atom is at its equilibrium of d, then the electric field is proportional to d to the n plus 1. And that means that d is proportional to e to the square root, or 1 over n plus 1, meaning that the dipole moment, P, is proportional, because P is related to d just by the charge. So that means the dipole moment is proportional to the electric field, E, to the power of 1 divided by n plus 1. So if we want this to be a linear relationship, and if you think about what we had Kr, that means it was 1, m was 1. So 1 over n plus 1 is 1 over 2. So that's why we had a e to the 1/2. But if we want a linear relationship here, then we want m to be 0. Because if we plug in 0, then we just get 1 over 1, which is just e to the 1. So we get a linear relationship. So essentially what we need then is to get a linear relationship, we need the charge density to be constant, some constant, essentially, for equation 4.1 to hold. And it's saying that this is in the weak field limit. So in the weak field limit, that just means when we're very close to the origin, I think. So anyways, to recap, if we want our dipole moment to be linearly proportional, then our charge density function needs to be equal to some constant in this sort of weak field limit. All right, so I think that covers problem 4.3. If you guys do have any questions, comments, or concerns, feel free to let me know in the comments below. If you haven't already, please subscribe to my channel. Leave a like on the video as well. And yeah, I will see you guys on the next one.